Today we are going to start with the very important chapter of your syllabus, that is circle. Circle. So now, first of all, before I go for anything of class 10 syllabus, let me just go for a quick recap of what we got in class 9, because we have to refresh everything and then we'll start notifying or identifying the definition also. Let me start with the definition first, then we'll go for its property. So it might take around half an hour, but even then I have to refresh this. So let us start with the definition. Definition. Okay. So definition of a circle. First I'll write the definition, then we'll try to see what exactly is the representation. A circle is a collection of points in a plane which are at a fixed distance from a fixed point in that plane. So circle means actually it is a collection of points lying in a plane, and that points are such that it will be maintaining equal distance from a given point. Say this is the point, this is the given point. I want to keep it here, and then I want to fix a distance. Suppose this is the distance I fixed. So every time I want to locate somewhere a point here in the whole plane, this whole world, I have to just keep in mind that I should locate the point at this much distance from this point P. So let us just see where we can put the points. So I can put a point here, I can get here, I can get here. So likewise, I can get many points. Now gradually you can go on finding the number of points more and more and more. And then moment you go on increasing the number of points, it will be taking the shape of a curve. Of course, as I am doing it freehand, so it will not be taking exactly the shape of a circle. So whatever we get, this is the circle. So this is the idea of circle we have. Now here, whatever is a fixed point, we have this fixed point we have started with. This is called the center of the circle, and whatever is the fixed distance, it is called the radius of the circle. Radius of the circle. So these are the things which are very, very important and fundamental. So overall, if we go for a very perfect sense, the circle will be looking like this, where the center is here, and any line segment from here to this center is the radius. So this is what already we know. This is what already we know. And the length or outside the boundary is called the circumference of the circle. Circumference of the circle. So this is all about the circle definition. So from the definition only we can easily remember, easily we can identify that it has infinite number of radii, it has infinite number of diameter, and it has infinite number of chords. CHO. Nicely. Chords. So chord means what? What do you mean by chord? Chord means any line segment whose endpoints are on the circle. It's a line segment whose endpoints are on the circle. So, so many chords will be getting, right? So, I think I should not wait for this to be completed because you know this. I think I can proceed further. Go ahead, right? Okay. So now, just quickly, we'll be discussing the properties of circle. Properties of circle without writing notes or without writing any statements. Just we'll be drawing the figure, and from the figure we'll try to understand what exactly are the properties of the circles. So that is very very important to know. So many circles I'll be drawing. Right? So many circles I'll be drawing. This is a circle here. Now I'll just talk about. Okay, first let me mark the center. Center is here. So this is the center here. Now, what properties we can bear for this particular circle is that if we consider if we consider any R A B, this minor arc, then I can construct many angles produced by this arc at the circumference. This is one angle which we have produced at the point say P. Similarly, at the point R, I can construct again one more angle, right? And then see what will be the property saying. This angle, if I construct over here, then the property says these two angles, they are the angle at the circumference or remaining part of the circle produced by RAB, they will be equal. So that is very very important. Angle APB is equal to angle ARB. They are both produced by minor arc AB. So they are equal. That is one of the property. That is very very important, right? So next property, property number two. Property number two. Now here also we'll be getting this time angle at the center. This time we are going to take the angle at the center. Now we are going to construct one angle at the center by a particular arc. One particular arc is producing angle at the center, and that arc, if it produce one angle at the circumference, then what is the relation between these two angles? That is the another property. That is the another property. This is O, suppose this is the point A and the arc is suppose BC. This is the angle, we call it angle at the center, or rather we call it central angle. It is the angle produced by the same arc in the remaining part of the circle. So what conclusion we can write here is this: angle BOC is 2 times angle BAC, right? So this is one of the very important properties. These are the properties which we are going to have. I'm not discussing all those which are very very trivial properties. Number three, property number three. This property number three. In this property, we'll be having a idea of cyclic quadrilateral. That is also to be known, right? So that is very important. Suppose, sorry, suppose I have a cyclic quadrilateral drawn here. Cyclic quadrilateral means its vertices must be lying on the circumference of the circle. So I have considered a cyclic quadrilateral ABCD whose vertices are on S. Then what is the property here? That is very very important. If I have a cyclic quadrilateral, actually I am relating cyclic quadrilateral here because it is all these properties are proved with the help of circle. These two are the opposite angle. So in cyclic quadrilateral, these opposite angles are giving you a sum which is equal to 180 degrees. That means opposite angles of cyclic quadrilaterals are supplementary. So this is one of the very important property here, right? Now I want to extend this figure only so that I can go for another property. So in case of cyclic quadrilateral, if you construct an exterior angle, suppose this is the exterior angle you have constructed, just by producing the side BA in this direction, then what will happen? This particular angle is equal to this angle. This is the exterior angle and it is the remote opposite angle or interior opposite angle. So these two angles will be equal. So that also I want to conclude in the same figure only. So what I can get here, so to indicate I have to give a name. So exterior angle DAE is equal to interior opposite angle BC. So this is the another important property of circle, right, which is related to the quadrilateral. So you must know these properties, right? There are many other, but these are the prominence which will help me to work out the rest of the part. So if you have finished, so please indicate. I'll go for the next. And now immediately I am going to start with the portions which are related to class 10. Okay. So anyway, before going to the next phase, let me just tell you one more thing. It is very important part, which is actually many times we missed out. Suppose I draw a circle in this plane. Suppose I have drawn it. And I ask you a very simple question. If I draw this circle, totally in how many parts the plane where I have drawn the circle it is divided? How many parts of the plane where I have drawn the circle? So you see, many persons or maybe all of us will directly say or immediately say that there are two parts because one is the interior and another is the exterior. Interior means you are in the inside and exterior means you are in the outside. You are in the outside of the circle. But what about the car? Because these points will be left out if you only talk about interior and exterior. So here, when you draw a circle, actually your answer is 3. That means you have divided the circle in 3 parts. One is the interior, which is included or um, covered by the circle, the arc of the circle. Then the exterior, which is lying outside the circle, and the circle itself, the curve, right? So why am I mentioning it here? Because there is a very important reason which we have to prove someday, or we have to use to prove. So I'm just going to tell you. Suppose you take a point P here in the plane, in the plane, take a point, in the plane, wherever you have the circle. So what are the 3 possibilities? One possibility, the point may be in the interior. Suppose the center name I give as O. Then what can you say about distance OP? OP will be less than the radius if I said R is the radius, right? When it is happening, if P is in the interior. If P lies on the boundary, that means on the circumference, then OP is equal to R. And if by chance P lies in the exterior, then OP will be greater than R. It's a very trivial observation, but remember, even if it is trivial, this is very important. Please mark it. In a better way, you can write. I did not write this. This is for the interior point. This is on the circumference, and this is for the exterior point. point lying in the exterior, always it is at a greater distance than the radius. So very trivial observation, but it is a very useful one. Where I'll be going for that also when we'll be studying with class 10 syllabus. So once you are done with, then we can. Okay. So we are now going to start actually with the class 10 syllabus idea. Right. So in the class 10, the first thing is the very first thing what we need to start with is your a line and a plane, sorry, a circle, a line and a circle in a plane. In the same plane, if we draw a line and a circle, what are the possibilities? Let us explore this. Right. So I can have the circle here. I can have a circle here, and then I can have a line here. Right. Rather, let me make it a better one because line has arrows. So this is one of the option. This is what one of the option I can carry. Next, what I can have, if I have a circle here, the line must be or might be intersecting the circle at two different points. And what else I can have? I can get a circle and I can get a line which never meet a circle. So apart from this, you cannot get any more situation. You may say sir, line is like this. Sorry, here one more. I did a mistake here. The third one is actually intersecting the circle exactly one. Yes, that would be the correct one. Actually, first and the third would be otherwise same. So here these are the three situations. Now what we can say, this line may not be like this. It may be here, it may be here, but the condition is that it doesn't intersect the circle. This line may be like this. The condition is that it should intersect at two different points. This line may be here also. Condition is that it should touch the circle or intersect the circle at one point. So these are the only three possibilities you can get. This is one, this is two, this is three. Here, no intersection, right? No intersection. So it is not important for us, right? Not important for us. Now I'm going for the other one, which is very important for us. Say I want to name this point, this as A and this point as B. I want to name. What name I have given? I have given the name of the point where this line is intersecting the circle at two distinct points. It is intersecting the circle at two distinct points. So when we have such a circle, such a line which intersects the circle at two distinct points, then that line is known as secant. So this is a very important definition. Try to remember that secant. So secant is a line which intersects the circle at two distinct points. The points should be distinct. Now, what will happen? You say, this is the situation I want to carry. Now, supposing that this line I want to drag like this or like this, then what will be the situation I want to show you in the third figure? Because the third situation is that only. If I keep the line here, then I am getting a secant. Gradually, I am taking this line like this. It is still a secant. Only thing is that you try to observe in this particular position, the points of intersection are here. Distance between them is this much. Suppose I am taking the line little closer to the exterior of the circle. Then what will happen? Now what happens? You can see that the points which are intersection points, they are coming little more closer. So now once you carry on this process till both the points come so close that they overlap each other and you stop at that point, then both the points will merge on each other. And that's a very important crucial situation, right? In that particular time, this point I would like to name as suppose P. This P is known as point of contact. This P is known as point of contact. But point of contact of whom? Point of contact of whom? Something must be there, no? What is that line now named as? This line is named as tangent. So these are the two very, very important concepts what we should remember. We should always remember that once the line intersects the circle exactly at one point, then that line is known as tangent. And if the line intersects the circle at two distinct points, then the line is a secant. So out of these three possibilities, these two are very, very important, right? So we have the definition also. So there may be a question that a line can intersect a circle maximum at what point? It is 2 points. Minimum at what point? No point, 0 points. So this is what. Please go through. Okay. So now immediately we can start with a theorem. Very important theorem, right? And here only I have to take that idea of what I explained already. Exterior and interior, etc. Right? Theorem. The radius through the point of contact of a tangent to a circle is perpendicular to it. Perpendicular to it. I'll be explaining the meaning. First, you please write the statement. The radius through the point of contact of a tangent to a circle is perpendicular to it. Perpendicular to it means what? Perpendicular to the tangent. Okay, now what exactly is the situation? You have to draw a figure. So this is the circle we have drawn. There is a circle we have drawn, and then we need to draw a tangent to it. Say, suppose this with a tangent, this with a tangent, and very clearly you can identify the point of contact also. Let me identify the point of contact here. Suppose this with a point P. P is the point of contact, and then suppose center is here. Let me name the center also. Suppose this will a center. So we have considered a circle whose center is at O, and then P is the point of contact of the tangent, whose name also, if you want to give, this is so T, and this T dash. So T dash, T and T dash. T dash is a tangent, P is the point of contact. Now what I have to show, if I draw the radius through the point of contact, right? So radius means it is joining the center and through this. Then I have to show that this OP is perpendicular to T dash. That's the theorem, right? So now I'm just going to write the restatement, because in this I have to write the restatement with respect to the figure I created. Restatement. Let O be the center of the circle and P be the point of contact of a tangent T dash to it, right? to show that OP is perpendicular to DTS. This is what we have to write. So here, let me try to tell you, we should not get any construction. We can go for the proof. So how we'll do the proof? You see first. I'm going to consider except this point, one more point here, anywhere, maybe to the left of P or maybe to the right of P, any side, right? Any point you can consider. It is not necessary that you should consider in the right side or left side, any such fixed idea is there. So I want to consider the point here, suppose. The point I want to consider and the name I want to give is suppose Q. I have given the name of the point as Q. So I consider the point Q here. So observation you try to make. There is an observation. In this circle and this line, they have only one point is common. One point in common. Number one. Number two observation. The complete line TT dash except this point is lying exclusively in the exterior of the circle. In particular, if this point Q is different from P, it will definitely lie in the exterior. So what can you say about distance OP? Sorry, OQ. OQ must be always greater than the radius. It is always greater than the radius. And in fact, OP is the radius. That means OQ must be greater than OP. Right? So this is what we are going to make as a strong point. So after getting this point, you join this line also. Please complete the figure. Note whatever I have said or written. Then we'll proceed further. Okay. So now we are going for the proof. So you can write. Let us consider. Let us consider an arbitrary point. Arbitrary means a random point. Arbitrary point Q, say on TTS, right? Which is other than, remember, other than P. You have to consider other than P. Therefore, Q must lie. Q must lies in the exterior of the circle. Q must lie in the exterior of the circle. Therefore, OQ must be greater than OP. So you see what idea we have got earlier. Just I have shown you this in the previous slides. So this is what we did. We have observed. Now you again try to modify. Supposing that I consider the point here and someone else considered the point Q here. Do you find any difference in the observation? No. If R is considered here, then you can easily say OR is greater than OP. If someone considered here, then also still. Meaning is that this results what I have wrote here in 1 is true for every position of Q except Q and P matching together, right? So I can write which is true for every position of Q, right? Uh, not not same as P, except this P. Except this P position, for all this position, this relation is true. If it is true, what does it indicate? Every time you are getting the OP as the shorter one. That means overall what you can say. Therefore, OP is the shortest, right, of all the distances, right, shortest of all the distances of O, right? O means that center I'm talking about from the line PT dash. So what did we observe? OP is the shortest of all possible distances of the point O from the given line TT dash. And at class 9 already we got shortest distance is the perpendicular distance. So from here easily we can conclude that OP must be perpendicular to TT dash. Here we'll write since the shortest distance is the perpendicular distance, right? Please note it, and that's the proof. That's the proof. So we can write OP perpendicular to TT dash. I did not write the concluding step. You write that, but that's the proof. So if you have any question, you can query. You can raise the query, or else I'll go for the next one. So we'll go for one more problem today. Problem is one more theorem, and that theorem we'll do and we'll finish for today. That is theorem. The perpendicular at the point of contact of a tangent to a circle passes through the center. Perpendicular at the point of contact of a tangent to a circle passes through the center. Just the reverse of what we did. Just the reverse of the theorem what we did. So suppose let me draw the figure first, then this is a circle, suppose, and you have a tangent. You have a tangent. This is a tangent, suppose you have at a point. And now here I first name the center as well as point of contact, and distance we name it first. Suppose the tangent you consider is TT dash. It is T dash. Then the point of contact, suppose it is P, and the center you are considering for the circle is suppose. So we have these things, right? So now what exactly we have to do is to draw a perpendicular at this point. We have to draw a perpendicular at this point, and we have to show that this perpendicular passes through the center of the circle. This is what we have to prove, remember it, right? This is what we have to prove. We have drawn a perpendicular at P. So please draw a figure, and as in when you finish, raise your hand. Okay. So now yes, a restatement will write first. Let O be the center of the circle and P be the point of contact of the tangent TT dash to the circle, right? We join, sorry, not join. We are not joining here. We are going to draw a perpendicular at P, right? To show that perpendicular at P to TT dash passes through the point O, that is the center. This is what you have to write. We do not need any construction, right? We go for the contradiction method. We'll go for a contradiction method. First, let me write the complete proof, then you will write it, right? You do not now, right? Just observe and see. If possible, let the perpendicular at P does not pass through O, right? So what we did, if it is possible, we have considered that the perpendicular at this P to this doesn't pass through, right? We have to modify perpendicular at P to which particular line to T dash doesn't pass through. Okay. So now you see how we start the initiate the contradiction. So this is a line and this is a fixed point. So if the perpendicular at this point doesn't pass through O, it means that perpendicular must pass through some other point, right? There, obviously, perpendicular, if it is not passing through O, I'm just drawing a figure here. If I say that this perpendicular does not pass through this point O, that means perpendicular will pass through some other point O. This. So now here also that is the case. If it is not passing through O, then there will be definitely a point O dash, right? So through which this perpendicular will pass. So we will mark that point, right? And then we say that this is the perpendicular. See, it looks absurd, but we are going to do the things by contradiction. So I can write, then there must exist, there must exist some point O dash through which perpendicular passes. That perpendicular, right? Perpendicular passes. That is O dash P must be perpendicular to T dash. That is O dash P must be perpendicular to T dash. Right? This is number one. Now again you try to see, but O is the center of the circle, right? O is the center of the circle. इसमें तो कोई घपला नहीं है. It is center of the circle, and P is the point of contact of the tangent T dash. Therefore, OP must be perpendicular to T dash. OP must be perpendicular to T dash because the theorem one says right. So now from 1 and 2, what you will conclude? O dash P must be parallel to OP. अच्छा, O dash P and OP कैसे parallel होगा? Because O and O dash are different points, right? So this is a contradiction, which is a contradiction, right? Which is a contradiction. And why this contradiction arises? This contradiction arises because we have considered a wrong supposition. What was our wrong supposition? That means the perpendicular doesn't pass. That's all. So we will now say, but this contradiction, arises, right, due to our incorrect supposition, right? Incorrect supposition. अच्छा, इनकरेक्ट सपोजिशन क्या था कि ये परपेंडिकुलर ओ से पास नहीं होगा. इसका मतलब therefore, right, therefore perpendicular at P must passes through henceforth. That's the thing. Please note it down, and when you finishes, please inform me. Today, this is the last question. We'll see you on the next day. So once you finish, please raise your hand. Okay, so today we will finish, right? And we'll see you